In this video, we're going to look at using counting rules to determine probabilities. So this really represents the culmination of a lot of our work, because we worked on determining probability, then we developed a bunch of different counting rules, and now we're going to dump all of those in the same bucket. So first, let's look back at what we said probability was. The probability of an event E occurring is the number of ways E could occur divided by the total number of possibilities in the overall scenario. So let's say the overall scenario is drawing one card from a deck of cards. Well, then there are 52 possibilities in that scenario because there are 52 different cards in a deck. Let's say our event is drawing a king. Well, then there are 4 ways that that event could occur because there are 4 kings in the deck. So that gives us the probability of drawing a king from a deck is 4 out of 52, which reduces to 1/13. So that's what we looked at when we first looked at probability. And then when we added some conditions on probability, and we learned about keywords like not and or, and conditional probability and all that stuff. Then we kind of seemed to go off on a tangent talking about all these different counting rules with the fundamental counting principle and permutations and combinations. And now here we are back at probability, but here's the deal. When we're looking at our definition of probability here, in the top it's like how many ways can event E occur? That's a how many question, and when we looked at all our counting rules, that's what they were dealing with, was how many different ways things could occur. And then the denominator is also a how many question, because how many different total possibilities are there in this scenario? And so what the counting rules gave us were techniques for calculating some more complicated how many questions, so that we could bring that back around and use it for calculating the probabilities in these complicated scenarios. Let's look at an example. So with this question, what is the probability of having a 5-card poker hand with 2 queens and 3 kings? Now here, I always just try to draw out a schematic of what's going on here, and this just helps me get an idea of what kinds of decisions I need to make. So it's a probability problem, so it's going to be a fraction, and I know it's a complicated probability problem, so it's going to be a big fraction. Okay, now the bottom of that probability is how many total 5-card poker hands are there. Kings, queens don't matter. That's our event. The bottom is just how many 5-card poker hands exist. And I'm just going to put 5-card poker hands here. Now in the top, what I need to do is, this actually breaks into a couple different boxes. I need to figure out how many ways I get 2 queens. I'm just going to put a 2Q there, because this is just kind of my brain map, and 3 kings, so I'm going to put 3K there. Okay, so it's just kind of my brain map to figure out the pieces that I need to sort out. Now that bottom, I find the denominators routinely easier to figure out, and so I tend to do them easy because I put off hard stuff. I know it's not a great life habit, but it's true. So how many total 5-cards hands are there? Well, so when you have a hand of cards, it doesn't matter what order they're in. So we're dealing with a combination, right? And we have 52 cards. So basically we're saying if I have 52 things to choose from, how many ways can I choose 5 of them? So this is 52, choose 5. And that's the denominator. And, you know, we can work through calculating that out. But again, this is just kind of figuring out the inventory, so to speak, of what we need to calculate out. So that gives me my how many different ways I can have any 5-card hand. Now for the top, I need to figure out how many ways I can have 2 queens and 3 kings. And this is one of those what I call slots and slots. So we have 2 different categories. So we're going to do a combination for the queens. We'll do a combination for the kings. So for the queens, there are 4 total queens in a deck. And so that's going to be a 4C2. I about wrote a Q for queen, but it's a C because it's a combination. Because it doesn't matter what order you hold the queens in your hand. Some people organize their hands and then some people just don't. And it troubles my soul. Now, with your kings, again, we have 4 kings in a deck. But we're going to choose 3 of those. And then when we have these slots and slots problems, the way we put all of that together is by multiplying those results out. So that's the idea, is you kind of figure out your little boxes and kind of create a brain map of what all you need to figure out and then figure it out. I think that sometimes these cause trouble because people just dive in without thinking about what they're trying to find. So you got to stand back and think about what you kind of find. Now from there it's just calculation. So I want to talk a little bit about the strategies before we get to the calculations, because that mostly for most people boils down to calculator work. But the one of the other things that makes these super challenging is we've learned a lot with probability. We learned a lot with our counting theories, from fundamental counting theory, permutations and combinations, and all of that stuff can be on the table with these problems. And so it's about having a toolbox full of tools and knowing which tools you need to use to answer this question. And that's actually one of the things that math teachers love and students really don't like as much, is this idea of there's not one exact way. I'm not teaching you a process. I'm teaching you tools, and you need to be able to back up and look at your tools and know which ones are needed for this particular problem. So that's the general idea. There's no new tools to be learned in this section. It's just dumping all the tools that we've learned together into one problem. Now, before I calculate this out, I'm going to kind of go off on a tangent and contrast it with something else we did, which was the probability of multiple events. So we would do a problem like, what's the probability of drawing 3 kings from a deck? So P of 3 kings, something like that. And in which case, what we did was we did 3 fractions. And so we start with 4 kings out of 52, and then we go down to 3 kings out of 51, then we go down to 2 kings out of 50 and multiply that all up. So you can actually do the 3 kings question like we're doing the one up above, but not vice versa. So the big difference between the one in green and the one in red is that the one in green has 2 different categories. So it has queens and it has kings. And once you start getting those slots and slots, that's where you really have to go to your counting theory to sort it out. So you can do that with cards, where you do different types of cards in the same hand instead of just trying to get, 4 aces in a row. You're trying to get an ace and all 4 kings or something like that. When you're doing committees and you want to make sure you have a balanced committee, and so let's say it's a committee of teachers and students and it's supposed to be a committee of 6, so you want to make sure you have a committee with 3 students and 3 teachers. Now you have 2 different categories, so you have to do this slots and slots construction like we're seeing in the green there. So this really more complicated way of doing probability using our counting techniques becomes necessary when we're trying to finesse out a particular event where we have items of different categories. Hopefully that makes sense. All right, I'll do another example. Oh wait, I should calculate this out, even though the actual number isn't as interesting to me as the construction, but I'll give you the result. All right, so that calculates out to 24 over 2,598,960, which reduces to 1 over 108,290. And basically that means it's not very likely. All right, now let's look at another example. All right, a restaurant has 10 servers, 5 cooks, and 3 greeters. They want to form a team to consider changing the menu. What is the probability the team of 4 consists of 2 servers and 2 cooks? So again, I like to draw out my schematic. So it's probability, some big old fraction bar. The denominator is all possibilities. So as far as the scenario goes, what we're looking at is how to construct a team of 4. And then for the numerator, this is where we do our specific event. So here our event is 2 servers and 2 cooks. So that means I need 2 boxes. One for my 2 servers and one for my 2 cooks. So that gives me the schematic of what I need to figure out. And so then it's just a matter of figuring out how to figure out the how many for each of those boxes. And like I said before, I always think that for these complicated problems, the denominator is more straightforward. So how many different ways can we compose any team of 4 from 10 servers, 5 cooks, and 3 greeters? Any team of 4 from 10 servers, 5 cooks, and 3 greeters. Well, we have a total of 18 that we're working with. And we're choosing 4 of them. So that's going to be 18, choose 4. Now for the top, we have to figure out how to get 2 servers. Well, 2 servers out of 10 servers. So that's going to be 10 C2. And then 2 cooks out of 5 cooks will be 5 C2. Fundamental counting principle tells us to multiply those two together. So that's how all the pieces go. So I want to emphasize there that I included the greeters in the denominator count because all teams of 4 would include the possibility that some greeters got on the team. But my specific event for the probability does not include the greeters because the specific event is 2 servers and 2 cooks. So hopefully that helps you see how to use those numbers to determine different things. I just encourage you guys when you do these problems that you don't just try to jump in. I really think it's uber helpful to get your game plan going. And what I mean by that is to build a schematic of what you want to figure out and then figure out how to figure it out. Go ahead and give some of these a try and see how you fare. Oh wait, hold on. You guys want me to calculate out the total. Alright, so with the numerator we get that that's 450, the denominator calculates out to be 3060, and if you divide a 90 out of both of those it reduces to 5 over 34. So I was thinking about something while I calculated that, and that's the idea that I'm growing increasingly concerned about everybody's tendency to just jump and grab a calculator real quick with these. And this is why I really like to teach the whys, because some of this stuff you just don't need a calculator for. So 10C2, that is 10 times 9, which is 90, divided by 2 factorial. So 90 divided by 2 is 45. So that's 45. Okay, 5C2, that's going to be 5 times 4. That's 20 divided by 2 is 10. So 45 times 10 is 450. So it looks like this intimidating thing, and sometimes combinations and permutations are really challenging to, and you would want to calculate them out in your head. But Sometimes they're not that bad, and it's actually because these are so cumbersome to punch out on the calculator, can be a time saver just by thinking about what it is, and some of them can calculate out real easily without a calculator. Anyways, that's my little commercial interruption about living a calculator-free life. Go ahead and give some of these a try and see how you fare.